Alright, so last time we talking about how to find from information about the electric potential, how to find information about the electric field, right? So the idea was that if you had a set of points in space, so that this is the x-axis, that's the y-axis, and you're given information about the electric potential at different points. So I did it great last time. So let's say that along this line, your electric potential, let's say that it was measured to be 30 volts. Let's say that along this line, you have 20 volts. Along this line, let's say 10 volts, 0 volts, minus 10 volts, minus 20. And the question is, what is the electric field, or estimate the electric field at this location? Okay. So how do you use that information about the electric potential to figure out the electric field? So the general idea is that you would take, if you wanted to find the components of the electric field, right, let's start with that. If you wanted to find the components of the electric field, say along the x direction, what you would do is you move along, you take 2 points, let's say that this is point 1, this is point 2, point 3, and point 4. And you look in the x direction, you see how the electric potential changes when you move along the x direction. So how does it change when you go from 1 to 2, right? So we know that from the definition of electric potential is the integral of the electric field multiplied by dotted product with the displacement vector. And if we're talking about the difference in potential between 1 and 2, you're going from 1 to 2. Your path takes you straight from 1 to 2. That's your delta S, as we talked last class. So if you can say that the electric field does not change much between 1 and 2, you can approximate this very nicely as a constant minus a constant electric field multiplied by the length of your path as a vector, going from 1 to 2, right? Delta S going from 1 to 2 is a vector that points this way. That goes that way. This is point 1, this is point 2. That's delta S, right? So if I move along the x-axis, delta S, it's going to be delta x in the I direction. So this number that I have here will be minus delta x E sub x, because E dot I, right? E dot I is E sub x. And delta x is just a constant number, some number is a scalar. So that means that if you move along the x direction, and I'm going to denote that by a little x here to remind you, because 1 and 2 doesn't tell you much, divided by delta x, and I put a minus sign here, that should be approximately equal to the component of the electric field along the x direction. Right? So your electric field at that point that I'm interested in will have, it's a vector in 2 dimensions, so it has x component and y component. So the x component, you could find it that way if you were looking for the components. Right? Similarly, if you now take a path that takes you from point 3 to point 4, right? That's the neighborhood of the point where you're trying to find the electric field. Well, now you're moving vertically, right? So now if you look at the difference in potential between points 3 and 4, right? That should be approximately equal to minus E dot your now delta S vector points in a different direction. Delta S vector is now delta Y multiplied by the J hat vector. So this number ends up being minus delta Y times E sub Y, the Y component of the electric field, which then tells you that E sub Y, that component, can be found by taking minus delta V. I'm going to specify that I got the difference in potential by moving along the Y direction, divided by delta Y, right? So now I have 2 equations. The electric field component in the x direction is minus approximately minus delta V when I move in the x direction divided by delta x, and the y component, just to provide more cleanly what we got, is this, right? And if I had a z component, because the world is three-dimensional, as you know, then the z component, of course, will be found similarly. Minus delta v, you will move in the z direction, and it will divide by the distance that you moved. Now, these equations are approximate, as we said, because the exact calculation involves an integral, right? Unless you know for sure that the electric field is constant between those two points, which sometimes it might not be. So, but this is a good approximation if the 2 points that you're taking, your delta x or your delta y, are small, so that you guarantee that the electric field does not change much between those 2 points, right? So if you do that for our example over here, so we have, I had given you some numbers last time. Let's say that this was 1 meter over here. And let's say that this is 1 meter in the y direction. So if we were to put in some numbers into this calculation, for the E sub x, the x component of the electric field, you will get, we're going to move in the x direction, and we're going to go from 1 to 2. So delta V is the potential at point 2, which is on the 20 volt line, minus the potential at point 1, which is along the 10 volt line. So that's 20 minus 10. 20 volts minus 10 volts divided by the difference or the distance between 1 and 2. That distance is 1 meter there. So this will be 20 minus 10 is 10, divided by 1 is 10, so minus 10 volts per meter. And for the y component, again, you look at the 2 points that you're going to use for that calculation, 4 and 3. 4 is on the 20 volt line, 3 is on the 10 volt line. So one more time, you have 20 volts minus 10 volts divided by the distance is also 1 meter, so you get again minus 10 volts per meter. So the x and the y components of the electric field at that location, we figure out that they are equal and negative. Both of them are negative. So now I can draw that vector. The vector electric field here, the best approximation to that number, will be a vector pointing this way. That is your electric field. Notice that it has negative x component and negative y component. And they are the same, which means that this makes an angle of 45 degrees. Right? Of course, it's no coincidence that you can see there that the electric field is perpendicular to the equipotentials. Okay, that is a general result that we derived or examined last class. It is always true that the electric field will be perpendicular to the equipotential line that goes along that point where you evaluated the electric field. Now we said these equations are approximate, and you can write an exact version of these equations if you take the limit when delta x and delta y go to 0. So in that limit, when you take the limit when delta x goes to 0, what you would have is an exact equation that says that Ex, the x component of the electric field, is the negative of the derivative of the potential with respect to x. And for Ey, that will be when you take the limit when delta y goes to 0, the previous expressions that we looked turn into derivatives. There is a problem in your homework where to find the answer you should take the derivative, because you calculate the potential of a ring along the axis that goes through the middle of the ring, and once you have the potential of the ring as a function of z, right, then from that you can get the component of the electric field along the z direction, which is just taking the derivative of whatever expression you obtain for the potential. Okay? So that is when you can take a derivative, because you know the function, the potential as a function of the variables. But if you don't know that, if you only know the potential at some discrete points, then you want to use the approximate expression we just discussed. That you take delta v, you divide by delta x, and you say that this is an estimate of your electric field in that region. Now it's important to be able to use this result, but in a more general case, which is in the case of a direction S in space. Okay, so remember that the expression delta V, I should stop writing in red, it's kind of annoying. Delta V is equal to minus, approximately equal, to minus E dot delta S, right? So if you have a vector delta S, say this is point 1 and point 2, your electric field makes some angle with that vector, whatever angle that is. This is your electric field E. That electric field has, you can decompose it into two components. The component of the electric field that goes along the vector delta S, I'm going to call that E sub S, and the component that goes perpendicular to it. I'm going to call that E perpendicular to S. Right? So this expression that you have here for the difference in potential between difference in potential when you go from point 1 to point 2, so V2 minus V1, well, you can write it as minus E sub S times delta S. Right? So what that expression tells you is that if you go from point 1 to point 2 in some particular direction in space, right, the component of the electric field along that direction can be found by taking minus delta V along that direction divided by delta S. That is the component of the electric field along that direction. So if you take the X direction, then of course S is X, and you're saying that EX is equal to minus delta V along that direction divided by delta X. If you take S to be Y, then that's the other. But this is the general result for any direction S that you choose in space. So there is an electric field pointing in some direction in space, and you move from point 1 to point 2. That determines your direction S, right? The difference in potential between those 2 points will be given by it's related to the component of the electric field along that direction. You can see that looking at it that way, it's very useful, especially for this problem in your homework, where you have, similar to what we just discussed, equipotential lines like this. Actually, what we just discussed is exactly that. So let's say that, go back to that problem. 20 volts for the equipotential here, 10 volts for this one, 0 volts for this one. And let's say that we want to find the electric field here. We just did that exercise, but I'm going to use it, I'm going to calculate that using this different direction, not along the X and along the Y, but I'm going to use something that I know already, which is that the electric field points perpendicular to the equipotentials, right? So what we did before was to define these 2 points, 1, 2, 3, and 4. I'm not going to do that. What I'm going to do is the electric field is perpendicular to this equipotential, and I know that it should be going from high potential to low potential. It's just like a river flowing from high ground towards low ground, right? So I know that the electric field should be pointing in this direction, perpendicular to the equipotential and from high to low. Okay. The question is, what's the magnitude? So the magnitude of that electric field, I already know that that's going to be my direction, delta S. I'm going to go from here to here, so that's going to be my delta S. Okay. So the electric field along that direction is going to be delta V, following that path, defined by delta S, divided by delta S, the distance. So if, for example, in your homework you were given this distance, say 1 centimeter between those two equipotentials, then your calculation is quite simple, right? From here you would get minus, the final potential is 0, the initial potential at the point where you started is 10 volts, and you're dividing that by the distance between those 2 points, 1 and 2 that you chose. So that is 1 centimeter. So that will be 10 volts per centimeter, which is 1,000 volts per meter. And that's it. You're done. You don't have to calculate the X component and the Y component. And if you're looking for the magnitude of the electric field, you will have to take the X squared plus the Y squared square root to find the magnitude, right? Here we're using the fact that we already know that the direction of the electric field is perpendicular and downhill. And so we're going to take that to be the S direction. and we look at the difference in potential along that direction between 2 points on that direction, divided by the distance between those 2 points, and that is your magnitude of the electric field. Go ahead. Okay, so when you're calculating a derivative at some particular point, right, what you want to do, the more precise way of doing it is taking a point on the right and a point on the left. That's a good comment. That is the more precise way, but sometimes you don't have points on both sides. If you have point only on one side, that's still okay. It won't be as precise, but you can still do that, right? So that's right. So to get a more precise result, I should have probably taken this point and that point. Right? But as I said, it's also okay to take this one, the point where you're evaluating the electric field, and the one next to it. Both are approximations.